Okay, so welcome back, everyone. So today it's my pleasure to welcome back Aamal Hussain, who will be giving us the sixth or the seventh lecture on dynamics and games. And today's stability of multi-agent learning in competitive networks. Yeah, thank you, Aamal.
Thank you. Sixth or seventh talk. I didn't realize there'd been so many, but for everyone who did stick for it, thank you for hanging around. Hopefully we have some good results to show you guys today. A lot of the results are quite recent, so we're quite excited about sharing them with you. So just to set up the scene, there's been a lot of work recently from the multi-agent system community, mostly from learning in games, that try to understand how the theoretical results from game theory can actually influence the design of more modern machine learning architectures. The most well-deserved example of this probably came out in 2020. This is a work from DeepMind where they were looking at how to learn a particular game, a game called Stratego. It's a two-player game, two-player zero-sum game. And they were trying to train an architecture in order to achieve superhuman performance in it. And they were trying to understand how can we use some of the results from game theory to apply in this context. The advantage of this is that the game is two-player and it's zero-sum. So if we look at the theory from learning in games, there's a lot of strong results in this setting. Most specifically, if you look at learning dynamics like Q-learning, fictitious play, policy gradient, these sorts of things, you can generally show and generally understand what the behavior of replicator or what the behavior of any learning algorithm is going to be in the case of zero-sum games. So as an example, if we take replicator and we run it on a really simple two-player game, it's just rock, paper, scissors. What you can see, and this is pretty well known in the literature at this point, is that for these zero-sum games, replicator does not converge to a Nash equilibrium. Okay, and that's what we're trying to learn, because a Nash equilibrium essentially denotes when agents can do no better than their current strategy as long as the opponent remains fixed, right? So in this case, the Nash equilibrium is set dead in the center of the simplex, so at the uniform distribution. But if you run replicator on it, it doesn't converge to it. Rather, the system cycles around the equilibrium. It only converges in time average, never in last iterator. So how do we resolve this problem? Well, if you look at replicator itself, what it's essentially doing, it's a very greedy system. It's taking any action I and comparing it with the average reward. So RKI denotes the reward for action I, and then we take the expected reward over the distribution. And we just say that if the reward for action I is higher than the average reward, then action I is doing well, and I should play it with a higher probability. Here, XKI denotes the probability with which agent K plays action I. So if it's doing well, we promote it. If on the other hand, it's doing worse than average, then this part is negative, and we demote the probability of playing that action. Right? So it's very, very, very greedy. So how do we deal with this? Well, one of the ways that they explored was, and this is actually pretty common in the literature, is to add a regularization to the rewards. In particular, if you add a entropy-based regularization, so this second term here now denotes the entropy of the relative entropy of the distribution, right? The distribution being the probabilities with which the agents play their actions. So we regularize it with this entropy. And this is all parameterized by this exploration rate or regularization rate, T, right? So now what happens if we apply this in a zero-sum game? So if we look back at replicator, we saw that it's not converging to a Nash equilibrium at all. But now when we apply the regularization, for any positive value of this parameter t, the dynamics immediately converge down to the Nash equilibrium. So this is good. We get to have convergence to an equilibrium, and it's guaranteed for zero-sum games. In fact, you can even add more players by imposing that they interact on a network. So this is called a network zero-sum game. And even then, you can apply any positive amount of regularization. So again, regularization being parameterized by t. So for any positive value of t, the system will converge down to an equilibrium. So this is good for zero-sum games. And in the example that I mentioned to you before, the game of Stratego, I mentioned this is a zero-sum game. So that was able to work there. But one thing that they were pointing out is that the behavior of learning outside of these settings, outside of zero-sum, isn't really well known. So if we take a look just empirically outside the zero-sum setting, all we've done here, if I compare the rock, paper, scissors game, right? So these are the rewards that each agent gets for playing a particular action. You can see it's zero-sum because each of these elements add up to 0. All I'm going to do is add a diagonal term, right? And these terms epsilon x, epsilon y can be very, very, very small. And what ends up happening is that the replicator system becomes chaotic rather than cyclical, right? And if we apply some regularization, let's say we apply some positive amount of regularization, this doesn't seem to resolve the problem. The dynamics, even though they're confined to a smaller area in the simplex, they're still not converging down to an equilibrium. So we haven't actually resolved the issue outside of zero-sum games. Now, this problem seems to become worse due to a work that was published in Nature in 2018 by James Sanders, Tobias Gala, and John Doyne Farmer, which essentially looked at the behavior of Q learning, or a variant actually of Q learning, in multiplayer games, right? So we've so far just been focusing on the 2-player setting. If we add more players into the game, what they were able to show is that as you add more players, the likelihood of these chaotic or complex dynamics become more prevalent. In particular, the amount of regularization that we have to add in order for the game to converge down to a fixed point seems to increase. Just for context in this heat map, the hotter regions denote the areas of parameter space where the dynamics are complex or chaotic, and these black cool regions denote where the dynamics end up converging down to an equilibrium. So you can see that as you increase the number of players, we have to increase the amount of regularization that we add, otherwise we're running into these chaotic behaviors. So how do we resolve that? If we want to deal with a multiplayer system, which is generally quite useful, we'd like to be able to stabilize the system without having to throw in a large amount of regularization. So to resolve that question, we actually looked at a limitation of the work of Sanders, which was that in their work, they assumed that the payoff for every agent, any given agent, is going to be dependent on the behavior of everyone else in the system. Okay, so in a 3-player game, for example, the player for any given agent is dependent on both other agents. What this doesn't take into account is that there could be a structure to how agents interact with one another, right? In particular, in general, social systems, whether they be computational or whether they be economic, they interact on underlying communication networks. If we think about this from a computational perspective, if we have multiple agents, there is generally a communication graph which dictates how those agents interact. In fact, we can enforce how those agents interact, either through nearest neighbors or some other topology. In economic settings, these would refer to social networks, whether they be online, whether they be in person. Any given agent is only going to interact with those other agents who they're connected to in this communication graph. So what we're now focusing on is, if we impose this underlying network interaction, how does the structure of the network affect the stability of learning, right? Whereas before, Sanders was looking at this specific setting where everyone's interacting with everyone. In that case, then every agent is interacting with all other agents, in which case you would expect that the stability decreases as the number of players increases. But if each agent is only interacting with two others, then there's no reason why the the amount of regularization that they need should increase. So this is our intuition. Now we're going to formalize that a little bit. Just out of interest, are there any questions so far based on what I've said? Feel free to interrupt me, by the way, at any point. No, okay. So to formalize this, we're going to take the setting of a network game, specifically a network POLYMATRIX game, but I'm just going to call it network games from here on out. In that, we have a set of agents, a set of edges, which denote which agents are connected to one another, and we have payoff matrices. So in the two-player case, this just comes down to a bimatrix game, but this obviously just generalizes to the case where you have multiple agents. And then the reward for any given agent is just going to be the sum of their rewards, or their rewards summed up along each of their edges, right? Now, in order to analyze competitive games in general, we need a way of parameterizing it, because as we've said, zero-sum games form a particular subset of competitive games, but it doesn't cover the majority of games. Even the example that I showed before, where we added the diagonal element to the rock, paper, scissors game, that is still a competitive game because the choice of epsilon is quite small, but it doesn't satisfy the zero-sum assumption anymore. So we need a way of understanding competitive games without invoking some zero-sum assumption. So how do we do that? What we do is we assume that the payoffs that each agent receives are correlated with that of their neighbors. So in particular, we can imagine that the payoffs are drawn from this from a large multivariate Gaussian, where the expectation of any given payoff element is just zero, and any the variance is one, so it's just a unit. A normal distribution there, but the correlation between any pairs of agents, so the strategies or the actions of any pairs of agents, those are correlated by this parameter gamma. So what does gamma represent? It essentially just measures how correlated opponent payoffs are going to be. If we take the limiting case of gamma equals -1, then we have a purely zero-sum game, because the payoff for agent K is going to be exactly negative of that of agent L for any of their strategies. But then if you have gamma equals 0, then the payoffs are completely uncorrelated with one another. So what this assumption allows us to do is take averages over ensembles of games and understand the expected behavior of learning in the average case, right? So to perform this, these are the steps that we take. We assume that the payoff matrices are drawn from this Gaussian, where the payoffs are correlated given by this parameter gamma. And so we're going to take the average over possible payoffs that are drawn from the same value of gamma. In the language of statistical mechanics, this is pretty common if we frame the learning system as what's called a disordered system. Now, a disordered system essentially includes a random variable which is fixed at the start and then held constant for the rest of the process, right? In our case, we fix a random set of payoff matrices, but then during the learning process, those remain fixed, right? So we're randomly allocating payoffs, but then keeping them fixed throughout the process of play. Now, using the tools from disordered systems, we can then analyze the average behavior. And at this point, once we get the average behavior, we can just apply the standard properties of linear stability to determine when the system is going to be stable and when it's going to be unstable. Okay, so taking this step by step, this is a lot. So what we do in the first step is we're taking the Q-learning dynamic, so this entropy regularized dynamic, and we're averaging over all games that are drawn from the same value of gamma, right? And that yields the following dynamic, which I guess is more of an SDE than it is an ODE. In this, what we have are a number of terms which capture the statistics of the Q-learning dynamic across the entire ensemble of games. So in particular, this eta denotes the time correlations between the probability that an agent chooses a particular strategy at time t versus at time t dash, right? And this is averaged over all possible Q-learning dynamics over the games drawn from gamma. Then this G just denotes the response function. So once again, the behavior of the Q-learning dynamics at some time t dash dependent on its behavior at time t. Finally, we have a normalization constant, which just enforces that all of these strategies have to add up to 1 so that everything just remains in the simplex, right? And most importantly, we have this parameter here, n0, which denotes the number of neighbors that the agent has in the graph, right, in the network. So for example, in the ring network that I showed earlier, the number of neighbors for each agent is 2, whereas in the fully connected network, it's n-1, so total number of players -1. Okay, so now that we have, are there any questions on the effective dynamics? Because I know that's quite a lot to take in one go.
I have a question.
Yes.
Is the number of neighbors fixed, or it could change?
No, we assume that the number of neighbors is fixed, because what we're trying to do is determine how the number of neighbors influences the stability of learning. So we keep it fixed throughout the process of play and then just analyze it afterwards.
Great, thank you.
Okay, so at this point, we're trying to determine the stability of fixed points of this averaged dynamic. Once again, this is a wonderful looking equation, but essentially all we've done is we've added a noise term. So it's just noise drawn from a standard normal distribution. And as a result, the dynamics are slightly perturbed away from the fixed point. So X bar denotes the fixed point and X tilde denotes the perturbations away from the fixed point, right? Now, what we'd like to do is understand the growth or decay of this perturbation. This is a pretty standard approach for understanding linear stability. Where we differ from the usual eigenvalue analysis is instead of doing the, taking the, determining the Jacobian and then analyzing its eigenvalues, we instead take the Fourier transform of this, or a linearized version of this dynamic, right? So, so that we just retain the dynamics in terms of the perturbations, take the Fourier transform. And the reason that we do that is because if we analyze the Fourier transform, which is given by this, if we analyze the Fourier transform at omega equals 0, then what we're able to do is ignore any transients and just analyze the long-term behavior of the perturbations. In other words, we're getting a sense of the long-term decay or growth of the perturbations x tilde. Okay, so in this step, all I've done is taken, well, actually I've combined two steps where first I linearize around x tilde, the perturbations, and then take the Fourier transform of that linearization. And then finally, we're just determining this at omega equals 0. And what we find is that in order, we end up getting this necessary condition for stability, so that in order for the perturbations to decay over time, this condition on the left has to hold. It's not a very intuitive condition, but there's a couple of important points that we need to take into account. The major point that we're trying to hammer in is that there's no explicit dependence on the total number of agents. Instead, all of the dependence is just based on the number of neighbors for each agent, right? Of course, embedded in this A is also the exploration rates and the fixed point, as well as gamma. So all of these things are going to play a factor. The exploration rate, gamma, and the number of neighbors are all going to play a factor. But we're mostly interested in understanding what the number of neighbors does. So with that, we're able to analytically find a necessary condition for learning to be stable in a network game. But in order to arrive at this analytic result, what we needed to do is analyze the thermodynamic limit. Specifically, we had to take the number of actions in the payoff matrices to infinity. So we're looking at the limit of large payoff matrices. And that's where this stability boundary holds exactly. Now, generally, in fact, in almost any game, we're not going to be dealing with countably infinite numbers of actions, or sorry, countably infinite action sets. We're going to be dealing with finite action sets. So with the caveat that this this condition is now going to overestimate where the stability boundary holds in finite action games, what we're interested in understanding is, does this statement that the stability only depends on the number of neighbors and not on the number of players, does that hold in finite games as well? For that, we turn to experiments. So specifically, we're looking at those two examples that I mentioned earlier, the ring network, where we fix the number of neighbors at 2, and the fully connected network, where the number of neighbors is going to increase as we increase the total number of players. So if we look at just the dynamics in a ring network for that initial perturbed rock, paper, scissors game that I mentioned earlier, where before we were getting these chaotic dynamics, as you increase the exploration rate, as we anticipate, the dynamics will eventually converge to an equilibrium. However, if you look at this same problem in the fully connected network, so where all agents have to interact with everyone else, the dynamics are firstly radically different, but most importantly, the amount of regularization that's required in order for the system to eventually converge down to that equilibrium is significantly increased, right? So whereas before we only needed t to be 0.35, now we need, in fact, for 0.35, the system still oscillates around the boundary. We need t to equal 1 in order to get convergence to a fixed point, right? So it would seem that a larger amount of regularization is required in the fully connected network than in the ring network. And in fact, we can see that again here. So in this plot, essentially what we're doing is we're taking 15 agents, running Q-learning with those 15 agents on this perturbed rock, paper, scissors game. And then seeing the spread of probability distributions as we increase the exploration rate. So for low exploration rates, it seems that the probabilities with which agents play their actions are spread out across the boundary of the simplex. But as we increase it, eventually there's zero spread, so the system has converged to a fixed point, right? However, in the case of a ring network, significantly less exploration is required, or regularization of the payoffs is required in order to yield convergence to a fixed point. So whereas before we needed, this is 1.9 as t in order to converge to an equilibrium, here we can stop at 0.6, so significantly reduced. And this holds in other games as well. So these were just two representative examples of games. If we look at more general classes, so here what we're doing is we're randomly generating network games, and then determining and then running Q-learning for a specific value of this regularization rate t, and then determining when the system has converged, right? And so in the, let's take the fully connected network. Let's take the case of 3 players. We can see that for low exploration rates, about 20% of these randomly generated games converged to an equilibrium. Sorry, around 20% of these games did not converge to an equilibrium. And then as we increase the exploration rate, eventually all of them converge to an equilibrium around about an exploration rate of 0.2, right? But the important point to notice is that as you increase the number of players, the boundary at which point we can guarantee convergence to an equilibrium, so eventually all of these games converge, this seems to increase as we increase the number of players. But in the ring network, where the number of neighbors for each agent is fixed, the total number of players doesn't seem to make a difference. Yes, it makes a difference in the sense that when we have these non-convergent behaviors, the number of games that do not converge seem to be higher for larger numbers of players. Now, this could be inherently due to there being additional complexity due to the increased number of players, but it could also just be because the size of the simplex has now increased. The joint simplex has now increased. So we're iterating over a larger state space, and so it may take longer for the system to converge. And so what's essentially just slow convergence is just being misinterpreted as no convergence whatsoever. As to which one of those cases is true, the answer is we don't know. But the important point to notice is that when they do converge, when we have the stability boundary at which point all games converge, in the ring network, they all happen at the same value of the exploration rate, right? So this, in a sense, is empirically confirming the analytic result. Remember, the analytic result only held exactly in the limit of infinite actions. So very, very large payoff matrices. But here we're running games with 20 actions, which is large from an experimental standpoint, but obviously nothing compared to the analytic assumption. But the basic premise or the basic result seems to hold independently of whether we're dealing with an infinite or finite action space. Just to understand that a little bit better, we added in an additional example, the star network, where now the network is heterogeneous in coupling. So before, we've always been assuming that agents have the same number of neighbors. Now we're taking the case where one agent is connected to all others, but every other agent is only connected to that one, right? And if we just look at the spectral properties of the adjacency matrix, you can see that there's a dependence on the number of players in the game, but significantly reduced to that of the fully connected network. So now we're trying to understand, okay, we know that in the ring network, we don't need, sorry, the number of players doesn't affect the stability boundary. So the stability boundary being at which point all games converge to an equilibrium. So for the ring network, the number of agents doesn't make a difference. For the full network, there's a linear rise with the number of players. But it seems empirically that for the star network, where we've got these heterogeneous couplings, the number of players seems to make an impact, but not as strongly as it is in the fully connected network. So it seems to be the case that somehow there's more deeper insights to be gained by understanding the actual spectral properties of the adjacency matrix that defines the network. So with that, we have essentially all the results that I wanted to tell you guys about today. The main thing being that the stability of learning does not depend on the total number of players explicitly, as was found by the work that I mentioned from Nature in 2018. Rather, it depends on how those agents are interacting with one another. What that allows us to do is take systems that ordinarily wouldn't converge because there's too many agents, and just constrain how those agents interact with one another. And all of a sudden we can guarantee convergence to an equilibrium with low regularization rates. Some of the future work that we're looking at the moment, I mentioned before that it seems that these heterogeneous networks seem to have deeper properties in terms of how stability depends on the structure of the network. So that's something that we're analyzing at the moment. And also, so far, we've been looking at necessary conditions for convergence. So this tells us that the necessary condition doesn't immediately tell us that the system has converged to an equilibrium, but just rather, if it's not satisfied, then the system can't converge to an equilibrium. So we're also looking at sufficient conditions so that we can immediately say to, for example, a practitioner, if we set the exploration rate at this value, then we can guarantee convergence to an equilibrium. So those are the two advances that we're looking at the moment. Thank you all for listening. And if you have any questions, let me know.
All right, thank you very much. Thank you. Any questions or comments?